Hello, I'm David. This is a Maths Learning Centre revision seminar for Maths 1A. It's semester 1, 2024. Hello from the past to those watching this in the future. I've had several requests, and we're going to start with talking about improper integrals. So improper integrals are a kind of definite integral. That's the first thing to know. So a definite integral looks like this, right? There's a number at the bottom and the top. You've got a function here, dx, and it might be an f of t dt or f of u du. But a definite integral has numbers here, has limits here. And the answer for a definite integral is a number. So equals a number. And an improper integral, either one of these places isn't a real place, or this function isn't defined at one or both of those places. That's the an improper integral. So improper when a is minus infinity, or b is infinity, or f of x is not defined at a and or b. And sometimes that just means that the whole integral doesn't have an answer. Sometimes it does. Because limits, it's basically the idea. Yeah. So probably best to just run through some examples, I think. That's the easiest way to make sense of improper integrals. Right. Hope that this works. May or may not work, but I'm going to give it a go. So this is definitely an improper integral because that location isn't real. Like you can't go to infinity. You can go towards it, but you can't get there. And so that's not a proper location, and so this is an improper integral. The function is defined everywhere when x is 1, and it's defined at all the places from here out to infinity, and so that's okay. And the way to deal with this is to figure out what it would be if you did stop somewhere, and then do the limit of that as that thing goes to infinity. Okay, so this is, if it exists at all, it is the limit as the top end goes to infinity of this. So you do the integral up to a particular spot and figure out what that answer is, and then see what happens as the particular spot goes to infinity. Does this look familiar? Good. I'm just checking to see if I'm matching what's actually in this course, because I teach help a lot of people learn in a lot of courses, and sometimes I don't always match up with what's in this one. I do a lot of Maths 1B. It happens 3 times a year, so sometimes I forget. And so this limit is going to stay here the whole way through my working until this has been figured out. And so now, from now on, I'm going to just ignore that limit. I'm going to try and figure out what this is. And the easiest way to do any integral is to write it as x to the power of something. That's the simplest one to do. And so I would do this. And then I would put my exponent up by 1 and divide by the new exponent. That's how you do a definite integral. And so So minus b to the -1 minus 1 to the -1. Me, okay, sure. And so I get 1 minus, and that's 1 over b. Cool. So now that I figured out what the integral is, now I can do the limit as b goes to infinity. And as b goes to infinity, 1 over b becomes 0. I warn you, please never write 1 over infinity. It's not a real thing. Yep. Well, infinity isn't a number. And so you're officially not allowed to divide by it. Some mathematicians think it's okay, but some of them are a bit funny about it, and you never know which one's going to be your marker. And so I would recommend to just write 0. Do the limit of 1 over b as b goes to infinity, and that answer is just 0. And you don't have to write 1 over infinity anywhere. You can keep it in your mind. So we're thinking this. That's what we're thinking. But that's what we're not going to write that. Some mathematicians think that's okay, and some of them don't. So just, yeah, because infinity isn't a number. It's a location, and you can't get there. So numbers are locations you can get to. Okay, so there you go. This integral is 1. And, you know, I really should have right at the beginning thought about this. 1 over x squared, 1 over x looks like that. 1 over x squared just faster. And that's telling me that if I color this in and keep coloring it in forever, then the total amount of ink there is graphite is 1 unit of area. Cool. Nice. Great. So sometimes when you get to this point, that limit doesn't exist. And that means the original integral also does not exist. And it usually doesn't exist because that limit goes towards infinity. Sometimes it doesn't exist because that limit flips and flops back between a positive number and a negative number. And so it doesn't really come anywhere. So cool. That is your classic improper integral. And why would they want you to know improper integrals? Well, some things you're interested in what happens if you do it forever. Because it's actually easier than trying to figure out what happens if you only do it for a short time. And sometimes you have to do integrals when you're doing probability theory, because the normal distribution theoretically has, for example, can be any number positive or negative to infinity and minus infinity. And so if you want to integrate something, sometimes you have to go all the way to infinity to get your probabilities right. So they're putting this in this course so that if you do a course called Probability and Statistics 2, or a matching course in some other degree, you'll have seen it. And they'll say, you've seen this, and they'll assume you just know everything about it, even though it will have been like 8 months ago. And yeah, so there you go. So that's why they're there. And another example, which I'm always bad at, is ones where the function doesn't exist there. So, give me a second. So what's that? Yeah, but that integral doesn't. Well, okay. So this is definitely an improper integral, not because these places aren't real places, but because, well, for the purposes of this function, they're not real places because I can't put 0 into that spot on the bottom. So this is an improper integral because since 1 over x is undefined for x equals 0. And if I wanted to do that integral, I need to say, well, I'm going to go at some starting point up to 1. and do the limit of as that starting point goes to 0. So this would be the limit as a goes to 1. Some people like to use t, but I have a very strong connection in my brain to this being from a to b, and so I like to call an unknown bottom end of an integral a. Yep. Oh, 0. Thank you. And officially, it's a going to 0 from the positive side. Because I don't really care whether I'm going from the other side, because my integral is just this bit. That integral there. So I'm definitely approaching 0 from that side. Is that a notation you've seen before? Yep, okay. Yes? It says 0 plus because I'm coming towards 0 from the positive side because I'm inside this area here, and I'm going from a to 1 and moving a backwards towards 0, so the a is coming from that side. I don't care what happens if a comes from this side because that's not the area I'm calculating. I'm on page 3. Okay. It is bad practice to do what I'm about to do, but I'm going to do it anyway. I'm just going to write equals at the top of this page. You should never write a lonely equals at the top of the page. You should always copy the previous line. But I'm going to do it anyway. Sorry. Yeah, you're supposed to write the thing that you started with and then an equals. But sorry. So well, I know what the integral of 1 on x is. It's ln of x. Technically, ln of the absolute value of x. That's not going to be relevant for this integral because I'm only using positive x's, but it is relevant for an integral on the other side over here. You would need the absolute values. That's an important thing. So this would be ln of 1 minus ln of a. And ln of 1 is 0. So I've got minus ln of a. Ooh, I have a thought. See that minus? That could come inside as a power of -1. The reason I like that is because 1 over is a really nice limit to try and calculate. One of the few that we have a good idea of what its answer is. So we have the limit as a goes to 0 from the above of, not ln, of ln of 1 over a. Okay, so 1 over 0 totally doesn't exist, right? If it was going to be anything, though it's not, because it's not a number, it would be infinity. And ln just keeps getting bigger as its input gets bigger. Ln of infinity is infinity. So in our minds, though we're not going to say it, ln 1 over 0, 1 over 0 plus, that's infinity. And ln of infinity is infinity. That's what we're thinking. And we're just going to say, does not exist. Yep. Well, I shall ask you, how many zeros fit into 1? That's what 1 divided by 0 would mean. Like 1 divided by something would be how many of the somethings fit into the 1. So how many zeros fit into 1? Well, as many as you wanted, and you would still never get to 1, which isn't anything. But also, 1 divided by 0.00000000001 would be a fantastically huge number. And 1 divided by that, but with even more zeros, would be an even more fantastically huge number. So the closer you get to 0 on the denominator, the bigger this answer gets. 1 divided by 0 coming in from the negative side would be minus infinity, by the way. Yeah. Okay, and so that does not exist. And it's totally okay to just say it does not exist. So this limit doesn't exist. That area As much as I can imagine coloring it in, if I tried to, I couldn't. Yep. Sorry. With the other one, we got 1 over infinity, which is 0. This one was 1 over 0. This one was 1 over 0, which is infinity. That's the problem. Also, even if I did this from 1 to infinity, it would still have been undefined. 1 over x is the closest you can, like 1 over x is the one that just becomes undefined. If I did 1 over x squared, it's defined. 1 over x cubed is fine. 1 over x to the 1.5 is okay, but 1 over x is bad. So 1 over x to the 1.0001 is okay, but 1 over x is bad. It's just that it comes down at a speed like this, at a speed that is just not fast enough to counteract the fact that the area is growing. So one of the puzzling things about maths. And it's just the way it is. That's why 1 over x is so weird. One of the reasons why 1 over x is so weird. And it's one of the things that causes ln to be so weird, because it's the integral of 1 over x. So yes, it is puzzling. Hold that puzzle to yourself. So sometimes that integral, that limit will exist, and sometimes it won't. And it will not always be, sometimes when you go to infinity, it won't exist. Sometimes when you go to a proper location where it's undefined, it will. They are all possible. But I can't think of any off the top of my head that go to those places. Yep. Yeah. So yeah, these are improper integrals, regardless of whether they exist or not. So even if it does come out to an answer, it's still an improper integral because of the fact that there was an infinity in the limit in the first place. Cool. All right. Some lecturers are okay with you writing equals infinity here. Some aren't. You should look at what's in your notes. Whatever's in the course notes is the thing that the people who are marking the exam will have to accept because it's in the course notes. Yeah. I'm going to do one more. Improper since 1 on x is undefined at that spot. Yeah. I'm just going to repeat that. It's really important. It's improper when the endpoints are infinity, or where it's not the function is not defined at one of the endpoints, or both. Okay, I'm going to do one more because it does match up with this population growth sort of thing. See if I can remember this example. It goes something along the lines of a radioactive emits. What do they do? There's alpha, it's beta particles. I don't know, alpha. I can't remember what they are. Anyway, let's just call them particles. No, I'm going to have to look it up. I'm going to get it wrong. Is there one in the notes? Ah, that's all right. No, I'm going to keep it. I can do it. See, look at this. This is like so much more impressive than what your lecturers do because I don't get to prepare. Yep. Yeah, yeah. I'm going to do it this way still. A radio of substance emits particles so that the number of particles per hour is given by e to the minus 0.1 t at time t in hours. It is extremely contrived. I don't know if it's realistic, but I don't care. How many particles are emitted for all time? Yay. So we watch this piece of radioactive, whatever it is, forever, and we count how many particles come out. That's great. So there are this many. This is per hour. No, I said it was per hour, didn't I? Particles per hour. So if there's this many particles per hour, if you multiply that by hours, it should give you the number of particles. So this is what I'm thinking. Particles per hour times hours should be particles. It should be. Yep, so we're going to have e to the minus 0.1 t particles per hour for this many hours. Teeny tiny span of time. And then we're going to add them all up forever. That is the number we're looking for. And this is a very physics way of thinking about it, and epidemiology and lots of other things too, is that you imagine a very small span of time and say, well, if this is the rate in that span of time, times that by the amount of time, that should be the total amount of particles, and then we add that up forever. Because this integral sign is an S. It really is, an S for sum. It was in fact invented before the sum notation sign. I mean, not before the Greek letter sigma, but sigma wasn't used for sum notation until after integrals were invented. So, yeah. So this S was a sum before the sum sign was a sum. Okay. And that integral is an improper integral because that's not a number. Now, it's perfectly well defined when t is 0, so that's okay. And the graph of this is like that. It goes like that on this side. It comes down at whatever rate it comes down at. And we're interested in this total here. Okay. So e to the power of t would, when I integrate it, be the same. But it's not a t, it's a constant multiple times t. So I'm allowed to divide by that constant multiple. So if the derivative of what's inside here is a constant, then you can just divide by that constant derivative. It's like the chain rule, but backwards. You're only allowed to do that if the derivative of this thing is a constant. If the derivative of this thing is not constant, you have to do proper substitution, which is one of the reasons why there is no formula for the integral of the normal distribution, because it's got an x squared in the top of the exponential there. So sucks, but this is fine. That's great. It's fine, I guess. I guess 1 divided by 0.1 would be 10. Yeah, because if I times the top and bottom by 10, I'll get 10 over 1. Okay, so I'm just going to do that because that's pleasant. That makes me feel better about this formula. If this had been a wickedly different, like 0.13, then no, no hope. But this is nice. I can do this. So I'm going to put in. Oh no, I'm not allowed to do that, am I? Being like a statistician. In the statistics course next year, they'll totally write it with an infinity in that spot, and that will be fine. But in this course, not so much. We're going to have to do the limit as b goes to infinity of this. Sorry about that, peeps. Because you're not allowed to sub infinity into anything. You can only do limits when there's an infinity. You see what I did here? I did it as a limit first. Yeah. Luckily, I realized if I was in an exam, I'd be going, phew, I didn't hand it in this way. Okay. All right. So the limit as b goes to infinity of minus 10 e to the minus 0.1 b minus 10 e to the minus 0.1 times 0. I'm being extremely explicit about how I'm subbing these things in. And the reason I'm doing that is that if I'm not careful, a lot of people, when they sub in 0, will just think the answer is 0, but it is not today, because e to the power of 0 is 1. So I've got 10 and e to the power of 0, which is 1. So that's this. So I've done 3 things simultaneously there. I've subbed in 0 into this to get 1. Maybe, yeah, maybe just to be absolutely clear, that's what I've done. And I've switched these around. And I've moved this e to the negative exponent to put that on the bottom. It's just easier for me to see what's going on if things are on the bottom of a fraction. So now, as b goes to infinity, so 0.1 times infinity is still infinity. And e to the power of infinity is still infinity. And 10 over infinity is 0. And so this is 10 minus 0, which is 10. It emits 10 particles. It's not very radioactive. But there you go. Fun. Okay. Yep. So let's put that reasoning in my thought bubble. 0.1 times infinity is infinity. E to the power of infinity is infinity. And 10 divided by infinity is 0. That was the reasoning I did. Yeah, e goes upwards extremely fast. E to the power of, so faster than any polynomial. Okay, well, eventually. Some polynomials go up pretty quickly, at the beginning, but not so much near the end. Right. How are we feeling about improper integrals? Yep. Oh, yes, it would be improper if at some point between a and b it's undefined. And you would have to split it into 2 separate integrals. I'm just going to make sure that we've got that. That's an excellent what if question. You should always ask those. What if it's undefined between a and b? Officially, you're only allowed to do integrals on functions that are defined everywhere on the domain that I mentioned there. So officially, that integral doesn't exist. But unofficially, you can still do it. So I've changed my answer. My answer is officially you can't do an integral on a function that isn't defined. Yeah. Sorry? But you could theoretically, so e.g. the integral from -1 to 1 and sine x over s, which I do not recommend attempting to integrate. It's not fun. It's not like the quotient rule has a reverse. That's not defined when x is 0. But you could turn it into that if you wanted. And they are both improper integrals. But officially, this integral actually doesn't exist because your function actually has to have a definition everywhere. on this domain, except possibly at the endpoints, in order for it to be an integral. But that would be something worth checking with the lecturer. Since it hasn't been mentioned at any point up until now, I wouldn't expect it to be in the exam, but it is worth thinking about. Yeah. This technically doesn't exist, but if it did exist, it would be this. Yeah. Okay. Because sin x over x looks like, and it has a hole just there, but it actually has a limit, which is 1. So, yep, was that? There are no dumb questions. What? This technically doesn't exist because the function doesn't exist when x is 0. That exists, but this officially doesn't need the function to exist at 0 in order to calculate these things. Like an integral needs the function to exist. I'm just going to put a inverted commas equals. An integral only needs the function to exist at all the places between here and here, and not necessarily at either of those spots. But if there is a place in the middle that it doesn't exist, officially, the function, the integral doesn't have a definition. Yeah. But I'm sure you could define integration in such a way that it did exist. But I choose to not worry about that today. Yeah. Okay. But if a lecturer asked me this in exam and asked me to calculate this and say, why is this not the same as that? I would say, it's not the same as that because this integral is defined since the function is not defined at an intermediate point. Something like that. Okay. Radio. Improper integrals. Great. Okay. It's time to talk about something else for a bit. I think we've done that well. I'm going to cop out on the rocket flight. I'm sorry. And the reason I'm going to cop out on the rocket flight, I'm still going to say something about it. The reason I'm going to cop out on that is because you don't have to remember how the rocket flight example works. I know that they examined it in a Mobius, sorry. The company that does Mobius changed its name and it used to be called Maple TA, so sometimes I forget. I know that they asked you about the rocket flight in one of the Mobius questions, but that doesn't mean they're going to ask you about it in an exam. An exam, extremely specific examples in general, from most my experience, from what people tell me about what happens in exams, are not in the exam unless they include all the information that goes in that example in the exam itself. But they may give you something that requires you to do an integral, but it won't necessarily be that exact problem or the population growth problem exactly as it is. But what they'll do is they'll set it all up for you so that in many ways, it's a reading comprehension task. You remember doing those at school, like in the NAPLAN, you get given a reading comprehension thing and you've got to prove that you understand the context and understand what it's saying. Well, that's what these questions are like. If you remember doing that Mobius on the rocket flight, what it required you to do was match up the terminology that was in the question with terminology that was mentioned in the written example and find the formula, the best formula in the derivation that went with that and use it. That's what I want you to hold on to as a thing you can do. You are capable of understanding the things that you read. Okay? And you can make sense of the things that you read. Keep track carefully of what the question says exactly every letter stands for. So just advice. Use your reading comprehension skills. Don't turn them off. They're there. And the maths ones, and so make sure that each terminology that's mentioned in the question, you go and find where it's mentioned in the instructions of what to do, that go find where it is in the text. Just be careful. There's a classic one, maybe coming in Maths 1B, which uses synonyms. It uses both the word coast and shore. And you have to know that they mean the same thing. So just keep that in mind. So there may be a bit of English comprehension as well. But I think overall, something that's already defined as a rate means it's a derivative. And if you would like to find the total, then you need to integrate the rate. So if you have a rate of, things per second, and it changes continuously as the seconds change, then the total things will be the integral from 0 to wherever of the rate dt. That's the basic idea of anything. Something that's a rate, if you integrate it by multiplying it by a d time, it will produce a total amount. Yeah, that's the big idea. I think that they're all based on. How do people feel about that and feel about me moving on from there? Yeah. Do please, if you want to talk through those examples, come to the Maths Learning Centre, sit down with one of the staff and say, right, here's the example. Can you talk this whole thing through with me? And we'll go, sure, that's great. Let's do it. But I just don't want to do it today. I'm sorry. Okay. Where are we up to? Actually, I do have one last thing to say. The point of the fundamental theorem of calculus is that the only things you can integrate are things that are already derivatives. It's just, you didn't ask for it, but here it is anyway. This is in this course, Fundamental Theorem of Calculus, right? It has two pieces. I can never remember which one is which, but the point of one of the parts of the Fundamental Theorem of Calculus, the part that goes like this, the integral from a to b of f of x dx is capital F of b minus capital F of a when little f happens to be the derivative of big F. This is saying that the only things we can actually do definite integrals of are things that are already derivatives of something else. That's what that says. I mean, we could do all the upper and lower sums and stuff and get an idea of what the number should be, and we can approximate it as closely as we want. But the only things we can do it with a formula are things that are already derivatives. And it's this idea here that a rate times a time is a total. You can only really integrate things that are rates. That's not actually 100% true, but they're the only things that really mean anything. Though you can't, yeah, don't get me started. Integrals are, excuse me. Hoping that's not an emergency. Yeah, Yeah, and I think that's a really cool thing about the fundamental theorem. It connects integration and differentiation, which until the theorem weren't connected. But yeah, you can only integrate things that are already rates of change, basically. It's really cool. If I'm getting, you know, that you can only that are already derivatives. The other half of the fundamental theorem of calculus kind of waters down my point a bit. Because the other half of the fundamental theorem of calculus says that any continuous function is a derivative. Yep. They're all little x's. Ah, that is a capital F that's pointy. I'll put them in bold. How's that? Cool. Okay. The other half of the fundamental theorem of calculus kind of waters down my point because it says every continuous function is in fact a derivative of something. I'm going to write it down because we have to put them. I can't do half of it. All right. So the other half said this is part. I think this is part 2 of the fundamental theorem of calculus. This is part 2. Part 1 says that if capital F of x is the integral from somewhere to x of little f of t dt, then the derivative of capital F is in fact little f. So if you define a function as the running total area of another function, like this is running total then it will be a function that has a derivative, and its derivative is this function. So that waters down the point. It's like you can only integrate things that are already derivatives, and it turns out most things are derivatives, as long as you define the function that it's the derivative of as an integral. It feels a bit circular, right? But that's okay, because, yeah, anyway, it is circular. That's the point. It's so fundamental, it's hard to know where the beginning is. But the thing is that definite integrals are independently definable without derivatives. You can define definite integrals with upper and lower sums. And so they exist all by themselves, even without derivatives. And it just turns out that they are connected to derivatives in both of these ways. I mean, yeah. No, that's it. I just want to say I really like the fundamental theorem of calculus.
Something about them being very self, just a rotation.
Yeah, little f is not the same as big F. It's whatever its derivative is. Yeah. Yeah. So antiderivatives are the same as running total areas, basically. Well, no, other way around. Running total areas are a kind of antiderivative. That's what this says. Though it is technically possible to find antiderivatives that aren't running total areas. So, which is mind-boggling anyway. So this function, the one last point. If you do have some wicked, weird function like that, that's my little f of x. And the little f of t, and this is the t-axis. And you start at a particular spot here, and you start adding up the area as you go, then what you can do is you can start making a new graph, which is the area so far. So when I'm starting at A, the area so far is 0, and then the area is getting bigger, but it's not getting bigger as fast here because the function's lower down. The amount of area you're adding is less here because it's lower. And so it goes like this. And then it starts to increase again when I got the area up to here. And it starts to increase again. And then it starts to not go up quite so fast. But the area is always going up as you move along here. And this function, its derivative is this. Yeah, that is how these two functions are related to each other. And you're also wondering, well, just a second, how can I get a function that's got negatives in it? Well, this one just has to dip below the x-axis, which causes negative areas, and that takes the total off. There's not really such thing as negative areas, but you can have negative rates of change. So if you've got a function which is a rate of change, dipping below the x-axis means that the rate of change is negative, which means the total is decreasing. And so, yeah, that's that. Okay. I have a question. Does the phrase average value occur in Maths 1A? Nope. Okay, then I won't talk about that. Cool. That's fine. I just wanted to, we've got enough people in the room so that if no one says it occurs, then it's probably true. So I won't talk about that. Okay. All right. What next? I have actually, I'm just going to have a 5-minute break and just check to see if this phone call is really important. So I'm just going to pause the recording